Okay, now we're going to look at the mechanisms for nucleophilic substitution reactions. There are two mechanisms, and they differ by the order in which the events occur in the reaction. Note we're doing a substitution reaction, so if we've got an alkyl halide and a bromide's a leaving group, another group has to come in. We're going to replace the bromide with this OC double bond OCH3, this acetate ion, as the nucleophile. And so the CH3 is our R group, bromine's the leaving group, acetate is the nucleophile. And there, one can imagine there are two possible ways for this reaction to occur. So if this is my alkyl halide, their carbon right here, and you say this is the bromine, this is the leaving group. Right now we've got the leaving group attached to the carbon. This is our alkyl halide molecule, and then here is the nucleophile. Well, the question is, how, when the molecules get together to do this reaction, how can the leaving group leave and the nucleophile come in and attack the carbon? And there are two possible ways that we can imagine. There are two possible ways that exist. The first way is that the leaving group leaves as the nucleophile is coming in. So we can get the situation where the leaving group here is on that carbon, the nucleophile is coming in, and as the nucleophile comes in, the leaving group leaves. Note, it's at the same time. So here we go, the leaving group is leaving, the nucleophile is coming in. We reach a point where they're about equidistant away, but it doesn't stop there, it just keeps going through that point. And then now we're getting this right here. Okay, so that's one way, one mechanism. The other mechanism would be this. The leaving group just plain old leaves, doesn't even need the nucleophile around. The leaving group just leaves, and then the nucleophile comes in. So the first way we're going to look at is this type of way right here, where the leaving group leaves as the nucleophile comes in. The second one we're going to look at is the leaving group just leaves, and then later the nucleophile comes in. All right. And because of the two ways these mechanisms are, because of the differences here, it leads to slight differences in the products and different ways how the reaction occurs. The first mechanism we're going to talk about is this one where the nucleophile comes in as the leaving group is leaving. We call this the Sn2 mechanism. So when we look at that, we have the Sn2 mechanism. Sn2, S is for substitution, and nucleophilic. 2 means bimolecular. And recall from Gen Chem 2, the kinetics chapter, bimolecular means there are two reactants in the slow step. Recall the slow step is the rate determining step. And in the rate determining step, the slow step of this reaction, there are two reactants. So here's our example reaction. If there are two reactants here, and we've got them right here, the rate law for the reaction is rate equals K times the concentration of our alkyl halide, we will call that the substrate, times the concentration of the nucleophile. This is a second order rate law. It is a second order reaction. And the mechanism looks like this. As we said before, as the nucleophile attacks the partially positively charged carbon, the Br minus leaves, and that happens at the same time. As this lone pair is attacking this carbon, this bonding pair is becoming a lone pair on the bromine. And if we get to the halfway point, we have this beast right here, the transition state of the reaction. So we're going to draw it with these brackets, put this little hash mark right there, the transition state symbol right there. But there's something that we're going to get into. Note, this carbon kind of has 5 bonds. Not really. It's got the 3 bonds to the hydrogen and 1 bond to the bromine. It's going to end up with 3 bonds to the hydrogen and 1 bond to the oxygen of the carbonyl, or the oxygen of the carboxylate here. But at this point, it kind of has 5 bonds. Really, it has 4 bonds because this is a very long half bond. You can consider this a half bond, and you can consider this a half bond. Note, the main thing happening until we get to this transition state here, where these two are about equal distance away, the main thing that's occurring is a carbon-bromine bond is breaking. That's where most of the energy is going into. And this oxygen-carbon bond is starting to form. When we get to the halfway point, before then, we're mainly breaking this bond. Afterwards, we're mainly making this bond, even though those two things are happening at the same time. But it's interesting to see what happens to these 3 hydrogens. Because note, with our molecules, when we have our original substrate here, our alkyl halide, these hydrogens, this is tetrahedral, these hydrogens are pointed towards the left here. But the nucleophile must come in from the right. And when we do the Lewis structure, we find that, okay, in our reactant, it looks like this. Our product is also tetrahedral. And so it turns out that as this nucleophile is coming in to form a bond, and as the leaving group is leaving, these 3 hydrogens here must bend so they're in a trigonal planar relationship, and then they flop over the other way. I can't do it with my models here, but this hydrogen would be bending back this way and then bending back further over here so that the end result would look like this. Okay. So, to reiterate this, what we mainly have at the beginning, here is our potential energy versus reaction progress diagram. Here is our transition state up here, where the nucleophile and the leaving group are about equidistant, not exactly. And it's mainly bond breaking. The main energy term happening, main energy factor happening at the beginning of the reaction is trying to break the bromine away, even though you're getting some of that energy back with that oxygen forming a bond to that carbon. The main energy is going into breaking that bond. And then once we reach a transition state, the main energy is we're getting back energy from making the bond. Remember, bond breaking is always endothermic, takes energy. Bond making is always exothermic, releases energy. And assuming that the nucleophile is a stronger base than the leaving group, that means our product will be more stable. We'll have a negative delta H. This reaction will go to the right. Okay. But note, as we said before, the nucleus must come in from the opposite side as the leaving group. We call this backside attack. Question, why can't the nucleophile come in from the same side as the leaving group? Well, it's actually kind of obvious. If the nucleophile is trying to come in this direction, it's going to run into the leaving group. If the nucleophile is coming in from the same side as the leaving group can't leave. It's got to be able to leave. The nucleophile would be blocking it if the nucleophile was coming in from any direction over here. And something also to remember, we have bromine as this tiny little figure right here. Remember, that's just the nucleus of the bromine atom. Compared to a carbon this size, a real bromine is a monster. A real bromine would be like this big as your fist, compared to a methyl group. Therefore, it's a really big thing, and the nucleophile coming in would just block that bromine from leaving. So the nucleophile has to come in from the opposite side. It has to come in from the back side to allow that leaving group to leave, since it's happening at the same time. We call that backside attack. And how does that affect the stereochemistry of the reaction? Well, let's look at this situation right here. Here we have a chiral atom right here. This is a chiral molecule. We have an ethyl bonded to the carbon, a methyl bonded to the carbon, an iodine, and a hydrogen. 4 different groups bonded to that carbon, including this iodine, which is a good leaving group. If we have a good nucleophile coming in, recall SH- is a really good nucleophile, it will do this reaction to make CH3, CH2, CHSH, CH3. Yes, we're just going to replace the iodine with the SH, but what about the stereochemistry? If we look here and we draw one of the enantiomers of this molecule in its stereochemical form here, all spread out. We see here's the iodide going out this way. We know the sulfur has to come in from the back side. We also know in the transition state that these three groups are going to be flopped back to where on the side the iodide was. And they just go flopping back. So note this CH3 is coming out towards us and to the right. After flopped back, it'll be coming out towards us and going to the left. CH3, CH2 is kind of down and to the right. It'll be down and to the left. It's just flopping straight over this direction. And so what we see now is that the SH doesn't replace the iodine in the exact same stereo configuration. It's on the opposite side. We have inversion of configuration. Always with an Sn2, the stereochemistry inverts its configuration. Okay, which means if we look at this reaction right here, we've got our leaving group chlorine, we've got a very strong nucleophile OH-. We know that the OH- has to come from the back side. It's going to essentially push this hydrogen up front because it's got to come in from the back side of this chlorine. Chlorine has to leave towards us. The OH has to be way back here and coming towards this carbon. Therefore, the stereochemistry the configuration is flipped here. Usually in a substitution reaction, like looking here, can we see that chlorine would be priority 1 if we were naming this molecule? We're naming this molecule, this chlorine is priority 1 if we're naming it R or S. Now this oxygen here is going to be priority 1 if we're naming it. And a lot of times, not always, but a lot of times, the nucleophile, the atom that bonds to the carbon, the new atom from the nucleophile, will be the priority 1 atom. Usually the leaving group is the priority 1 atom. So if this was, well, what is this one? 1, 2, 3. This is the S configuration. It converted to the R configuration, inversion here. But that's not always the case. Occasionally, the leaving group leaves, the nucleophile comes in, but if the leaving group were priority 1 and the nucleophile were actually priority 2 on the new molecule, then you might not get flipping R to S. So we cannot say that it inverts the stereochemistry. We cannot say that it converts R to S. It often converts R to S and S to R, but we can't say that 100% of the time. But we can say 100% of the time is an inversion of configuration. If the leaving group was coming towards us, the nucleophile is coming in, the nucleophile will end up being away from us. So for example, if we have this reaction here, draw the Sn2 product. If we have this as our molecule, we have this nice ring here, cyclohexane. Cn-, we know Cn- is one of our exceptions. It's an extremely good nucleophile that doesn't behave as a base. It's a very weak base, but a very strong nucleophile. So we know, okay, here's our good nucleophile. We can see bromine is the leaving group. None of these others are leaving groups. We see the bromine is going up this direction, which means the nucleophile has to come in from the back side in through here. Cn- got to come in through here, which means this hydrogen is going to get flipped up to where the bromine was. And Cn is going to be going down. Hydrogen is flipped up like that. The inversion of configuration. All right. So when we're looking at this Sn2 reaction mechanism, the one thing we find is that methyls and primary alkyl halides do very fast Sn2 reactions. Secondary alkyl halides do Sn2 reactions fairly slowly, and tertiary alkyl halides really do not go via the Sn2 mechanism. Tertiary alkyl halides, the reaction is way too slow for it to get anywhere. Why is this? Well, it's because of that backside attack. When the nucleophile has to come in from the backside, this carbon here is being kind of shielded by the 3 hydrogens here. And so the nucleophile has to get in there. Recall with our space-filling models, if we had this beast right here and you wanted to do a nucleophilic attack on this carbon right here, the nucleophile would have to come in and find that carbon, but it's kind of being blocked here. It's a little bit difficult to get to that carbon. Now, as long as there are hydrogens on there, in general, we are okay. It's not too hard to get to that carbon. But what happens if we have larger groups on there? Look at this. Now we have put a methyl group. Say this carbon buried down in here is the one we want to attack, but now we've got this methyl group and this CH2 blocking it, and this hydrogen, it's tougher to get in there. We've got a lot of steric hindrance trying to get into this carbon. If we put a third methyl group on here to make this a tertiary carbon, boy, it would be very difficult for a nucleophile to get into that carbon there if there were 3 methyl groups blocking it. So due to steric hindrance, due to blocking from that backside attack, tertiary alkyl halides there's too much stuff blocking that carbon for a nucleophile to attack it. So when you're dealing with Sn2 mechanism, we're mainly going to be looking at primary alkyl halides and sometimes secondary alkyl halides, but tertiary alkyl halides just will not do this mechanism. All right, the next mechanism we're going to look at is the Sn1 mechanism. It is the one where the leaving group leaves first and then the nucleophile attacks, and we'll look at that in the next video.